Hello, my name is Nathan Hutton, and I'm teaching the computer graphics course for Westminster University. So, this video is going to go over what the class will generally be about. I'll do a very introductory dive into a couple of general rendering concepts, and I'll go into what you need to know, or really more like what you don't need to know, to ease any apprehensions about taking what may seem like a very math heavy computer science course. First, let's talk about what I mean when I say computer graphics. This is not a graphic design course. You don't need any artistic ability whatsoever. And this class isn't going to help you develop any artistic abilities. This class is essentially just going to go over how we render things on the screen. Though we'll almost entirely be going over one specific way to do this called rasterization, which I'll get into in a bit. First, I'd like to talk about some applications of computer graphics. It's actually a very broad field. It's anything involving the generation, manipulation, and storage of visual images using a computer. We use computer graphics in video games, movies, CGI, animated movies, simulation, and even things like image filters on your phone. The last one is a good example of a subfield of computer graphics called image processing, but even games and movies and whatnot use image processing. This is a bit of a simplification, but generally there are two primary ways to render things: rasterization and ray tracing. If you're familiar with video games, you've probably heard of ray tracing, but in reality, almost all video games use rasterization. Even games that allow you to use ray tracing are almost always just allowing you to use a mixture of ray tracing and rasterization, though there are some exceptions to this now. What may be surprising is that ray tracing actually came first, at least conceptually. This is because ray tracing is very intuitive and easy to program from scratch compared to rasterization. But for a long time, it wasn't really something people could use because it was too computationally expensive. Ray tracing is a bit like when you're trying to make an algorithm or figure out some LeetCode problem, and the first thing you think of is the brute force solution, but you're not actually able to use it because it's computationally unfeasible. Ray tracing is where we really try to somewhat accurately simulate the way light bounces around, reflects, refracts, absorbs colors, the whole works. Just from that, you can probably begin to sense why we had to come up with something else if we expected our computers to actually finish rendering anything. Now, in real life, light is bouncing all over the place, and only a microscopic fraction of it reaches our eyes, which is what we see. So, from a computing perspective, we have all these light rays that aren't reaching our eyes, and they're a massive waste of resources. But how could we just single out the rays that reach our eyes? Well, thankfully, light is bidirectional, meaning that if you take some ray of light that's been bouncing around and you shoot it in the exact opposite direction, it will trace the same path, just in reverse. So, what we can actually do here is trace a bunch of rays coming out of our eyes or the camera perspective, whatever you want to call it, and just see how those bounce around and record the results in an image. To use a simple example, imagine we shoot this ray out of the camera and it hits this apple. We'll mark the pixel corresponding to that ray as red. Now imagine this ray hits the perfect mirror, then hits this banana. We'll make the corresponding pixel to this ray yellow. Obviously, this is a simplification. I mean, what if the ray hit the apple, but there was some object between the apple and the light source? Meaning the apple shouldn't really be visible because there's no light on it. The simple solution to this is to trace a ray from here to the light source and see if it hits anything on the way. If it does, then we say that it's in shadow. Now, in real life, if you want your ray traced images to look good, you're going to have to do a lot more with these rays. Additionally, you're going to have to shoot out several rays for each pixel, not just one, and you'd average the results together. A typical 1440p monitor has about 3.6 million pixels, so that's a lot of rays you'd be tracing. To give you some perspective of how expensive this is, in some ray tracing algorithms, when the ray hits the apple, for example, they'll actually have several rays bounce off of the apple in that spot, and they'll average those results together. Those rays could even hit something and have several rays resulting from the bounces. In the final project of a ray tracing class I took at the University of Utah, I actually shot out 100,000 rays for each pixel. And for each of those rays, we might let 5 bounce off of whatever we hit. And those rays then get to go do whatever we program them to do. So clearly, this is very expensive. This is why most video games don't use ray tracing, or At the very least, they have very limited ray tracing capabilities. Now, in this class, we're not going to be doing any ray tracing. We're actually going to use rasterization, which was created specifically so that the computer wouldn't have to do all this work. Rasterization essentially uses a bunch of shortcuts to fake the results, but it's been optimized over time so that the results are pretty astonishing and often indistinguishable from a ray traced counterpart. Unfortunately, this means that we as individuals have to do more work because ray tracing is actually pretty intuitive. It's what we would prefer to work with. It's just hard for our computers to handle. For a while, even animated movies didn't use full ray tracing, and they only had to make the frames one time. Toy Story is an example of this, actually. So, for Toy Story, Pixar actually made a rasterization engine with lots of creative techniques to get around the technical limitations while creating results that looked pretty much exactly the same. By the way, the co founder of Pixar actually went to the University of Utah, and this is going to be a recurring theme in this class. Rasterization is going to let us basically fake our results. We're going to take a bunch of objects made out of triangles, which is the shape that our GPUs are specifically designed to handle, and we're going to project them onto our screen. The first assignment will actually just be rendering a blank, flat color. Then after that, we're going to render a single triangle. Then from there, projects will obviously become more complex, but also a lot more fun. To be clear, you don't need a GPU to do computer graphics. For example, in that ray tracing class I talked about a bit ago, we did everything on the CPU, but our GPUs are designed to do computer graphics, and it's what we're going to be using in this course. But if you don't have a GPU on your laptop, that's totally okay. You'll just use the integrated graphics card on your CPU, which will be more than enough for the programs we're going to make. An integrated GPU is still a GPU. Now, why do we like triangles so much? I mean, even in video games, when you see something like a sphere, it's still made out of triangles. For example, look at this sphere from the game Portal. If you look really closely at the edges, you'll see that it's not really a sphere. Well, the nice thing about triangles is that they're always going to be flat in 3D space. If you take any 3 points in space and fill it out, it'll always be flat. Additionally, trigonometry is usually a lot easier to work with than whatever the alternatives are. This is a good time to talk about prerequisite knowledge for this course. You do not have to have taken trigonometry. In fact, I've never taken a trigonometry course, and I would not say I'm very good at it. It would be helpful to be good at trigonometry or have taken a course, but it is not necessary. Linear algebra is actually the most useful math in this course, but that also isn't a prerequisite. In fact, when I took computer graphics at Westminster, I hadn't taken linear algebra yet. I didn't even take calculus yet, which you won't really need for this course anyways, but I thought it'd be worth mentioning just to alleviate some nerves you may have, because I remember any mention of math when I was going through my undergrad made me a bit tense. Even if you have taken linear algebra, the linear algebra we'll be using in this course is probably a lot more geometric and intuitive than what you're familiar with. And I know that math is really daunting for most people. I am one of those people. I'm hoping that this course can introduce some intuitive math to those who've never found it intuitive, but I promise that I plan to introduce it in a non scary way. In fact, I never found math intuitive until I started diving into computer graphics. I'm actually making this video mostly so that you guys can reference the math, because I know that trying to throw it all at you in a lecture probably isn't going to work very well. The bottom line is that if you're scared of the math, just know that I was more scared and probably a lot worse at math when I took this course, and it was fine. And I even took this course without these videos and right before AI had taken off, which you can now use to help explain things when I explain it poorly. The last thing I want to mention is that I'll be bringing up math concepts only as they become relevant for the projects. So for the first couple projects, there really won't be much math at all. So I won't go over the math much. But for the project after that, there will be some fairly intuitive math. I will try to make it as undaunting as possible. And thankfully, these math concepts will carry us through most of the projects. If you haven't taken much math before and you think of it as this complicated abstract stuff, I want you to know that it will be geometric and there will be a visual component to all of it. So, how do we actually tell the computer to draw and manipulate these triangles? We're going to be using WebGL in this course, which stands for Web Graphics Library. We're going to be doing this because it's easy to use, and all your computers should be able to use it without any problems. This course will be fun to teach in OpenGL, but it's kind of a pain to set up, and Macs really struggle with it these days. This does mean that we're going to be using JavaScript, which you're probably all a lot better at than I am. So if you feel like you're not very good at JavaScript or haven't ever even used JavaScript, that's fine. I'm pretty sure that the first time I ever used JavaScript was in the computer graphics course from Helen. And if you hate JavaScript, we can just hate it together. This does mean that we're going to be rendering things directly in our browsers. I've heard mixed things about whether or not you need to use Chrome. I've had sort of mixed results with it. I try to use Firefox, but it's hit or miss. Most people will want to use Chrome. It's the easiest to get going. You should just be able to double click your index.html file or whatever you have, and it should just pop up in the browser without many issues. It might vary a little bit by operating system, but my plan is to have very little set up for this course. Now, to be clear, WebGL is outdated, but more modern graphics libraries like WebGPU, which I did consider for a second, is much more verbose. It's sort of like imagine if you wanted to make a program and you thought, well, I could squeeze a bit more performance out of it if I just used assembly, but obviously you're probably not going to do that. So WebGL will let us just focus on the fundamental ideas and algorithms without getting all tangled up in driver programming, which I'm not even familiar with at all, so I really couldn't teach it.